I'm very happy to introduce David J. Myers, who will tell us about the paraconstruction as a distributive law. Take it away.
Hi, everybody. And I just want to first start off by thanking Bryce and Tim for organizing this workshop. It's really cool to have a space to talk about double categories. I guess everyone probably just heard me, but it's a little bit late here, so I've been missing some of the previous talks, but I'm going to catch up on them on YouTube, so I'm really looking forward to that. And so this talk is in some ways a continuation of the previous talk that Matteo Capucci just gave. And so I had the pleasure of getting to hang out with Matteo and the rest of the Glaswegian group in Glasgow, the Strathclyde group, I should say, in Glasgow this summer. And Matteo showed me this diagram, which I've reproduced here. This is the triple category diagram from the end of Matteo's talk, drawn up a little more abstractly with some relabeling, and I just thought it was quite interesting to see and exciting to see a triple category in the wild with some motivation for it, and it's a very cool extension to the way I have been thinking about systems theory using double categories. And it's just a kind of a tantalizing construction, and I wanted to understand it. So the one thing that's sort of obvious to note about this, and this is if you've seen the para construction before, and if you haven't, don't worry, I'm going to explain what it is very shortly. If you've seen it before, this triple category really looks like the para construction applied to this double category of lenses that Matteo was talking about. And so so we set about trying to show that it was in fact just the para construction applied to that double category. And so we've done that in this way by viewing the para construction as a distributive law. And so this is joint work with Matteo, and I think it's a rather cute story. So I'm excited to share it with you all. So the plan here is to talk about the whys, the whats, the hows, and the wheres of the para construction. So first off, the why the para construction? Well, if we have a process theory, which as a first pass we could take to be a monoidal category, then in many cases we want to separate our inputs from the parameters. So some of our inputs will be parameters or control variables that we imagine as being set separately from the other inputs to our process. So you can, if you take the point of view of control theory, which always imagines its subject being a little factory, where you can imagine big boxes with conveyor belts coming in, the conveyor belts going out, stuff goes in, the process happens, stuff comes out. The control is the little wire that runs up to the room where all the engineers are, hitting the buttons, telling this machine what to do. Or maybe it's not engineers, maybe it's just a computer. But that's the idea of the separation, that those are inputs to the process as well, but they're inputs of a qualitatively different sort. So we separate them out. And this construction has appeared in studying neural networks from a categorical point of view, in cybernetics, as Matteo was talking about. So that's in control theory and game theory from a categorical point of view. And also it appears in the work of David Spivak and Brandon Shapiro on dynamic operads. So I'll talk about that and how the para construction is used in these settings. And so after I've told you why I want to do it, I'm going to tell you what it is I want to do. So the para construction is usually seen as taking, or was originally seen as taking a monoidal category and giving you a category. So it takes your monoidal category, which is your process theory, and it gives you a category, which are your controlled processes. But what we're going to see it is taking in an actegory, which is a fun name, I believe, due to Matteo and Bruno Gabrinovich, is an action of a monoidal category. And we're going to produce not a category, but a double category. And so this is sort of where double categories come into the story. And we're going to do this, we're going to end up in double categories for the reason a lot of us end up in double categories, which is that it's sort of natural for us to end up in a bicategory, but it turns out to be much nicer to work with a double category. That's sort of a theme, I think, of the conference, maybe, or this workshop. Okay, so then after that, we'll talk about how we're going to do the paraconstruction. So we're going to see it as a distributive law between pseudomonads in a certain tricategory of spans of categories. So this is a pseudomonad in spans of categories is a pseudo double category. So this is, we're going to get this distributive law between double categories. It's going to produce a new double category. And that's how we're going to build our paraconstruction. And so when we've reformulated it in this way, it will become clear that it's very abstract and that it can be performed in any suitably complete two category. You just need enough limits to be able to express the triple category we need and the various ingredients. And so for that reason, we'll be able to apply this paraconstruction, not just to categories, but to double categories themselves. And that's how we'll arrive with a category internal to double categories, and that's a triple category. And so that's how we're going to end up at our triple categories, and then we'll see that. And so the observant of you might notice that there's one W word missing from this, which is when the paraconstruction. The answer is not yet. This is work in progress. So why the paraconstruction? The paraconstruction was first defined, or the para, I guess I could say, was first defined by Fong, Spivak, and Tuyeras in a paper called backprop as a functor. And it was defined as just a category of maps whose objects were the Euclidean spaces and whose maps are parameterized maps between Euclidean spaces. So a map from Rn to Rm was a natural number k of the dimension of the parameters, how many parameters we need, and a function from Rk times Rn to Rm. In this whole talk, I'm going to be drawing my parameters in blue, and I'm going to be drawing my objects in green to help us keep track of what's playing what role. And so we could draw this situation if we were working in this monoidal category. The thing I want to focus in on, we're working in this monoidal category here of Euclidean spaces, and I said C naught, but it really needs to be C1. Sorry, it needs to be differentiable to run gradient descent. We're in this monoidal category of differentiable functions between Euclidean spaces. We perform this operation to equip our maps with parameters. And so we can draw this, this diagram here, which is the box. We see that it's a map from Rn to Rm, but it has this extra wire, which is this parameters. And indeed, the paraconstruction can be seen as a special case of the construction that Chad Metzger talked about earlier in the week, coming from the free cornering of a monoidal category. But I'm not going to use that point of view here. But these diagrams are precisely those if you thought they looked similar. So now, in that same paper, the authors also describe backprop as a functor. That's the title of the paper. And the functor lands in this category of things they call learners. And learners are these complicated Baroque-looking objects where they have two sets, and the learner between them is this extra set called the parameter space, together with these three maps. And the composition is a little confusing between these. Everything has to hook up correctly, and it's a lot. So, but the basic idea here is first we have the function we're trying to learn, which is I. And then we have the update function u, which updates our parameters given the input data, the desired output coming in on the B wire and the current parameter. And then it also has the selection that tells us how to select a new input to continue our training. So the idea is that this is an abstraction of what you need to be able to do an iterative sort of gradient descent process, or iterated learning process. So what's kind of wonderful is that you can see these learners, you can package them up if you know what a lens is. All this complicatedness with a lot of these wires flowing around becomes a simple thing, granted that you already know what lenses are, spent a while with lenses, so they feel very cozy. is a parameterized lens. So it's a lens of the form I have on the bottom left there. And these lenses, I probably should have put the definition up of lens again, but it was in Matteo's talk. A lens here has a map going forward on the bottom. And that's also a thing. I think that my conventions are different from a lot of other people's with these, but my conventions will be the ones I took in my book. So put things on the bottom, maps going forward on the bottom. So we have this map I on the bottom, which goes from P times A to B. And then we have maps going back on the top, but they're allowed to also use an input from the domain of the bottom. So we have a map. So as you can see, U and R both take in B, but they also take in P and A, and then they give elements of P and A respectively. And so we can wire this up and draw this diagram as on the bottom right, which is a shape we'll see a number of times here. So the cool thing about this paper is that it actually uses the para construction twice. So it's the first instance of it. It wasn't explicitly written there, but the authors all knew that it was this case. So now the other use for para lenses is not just in gradient descent, but as controllable or controlled systems. And so this is the sense in which Matteo was talking about it in the last talk. So in here, we have the picture again. This is just a para lens, but I'm going to read it with all these names. So we're going to think of this para lens as a controlled system. And so what we have here is we have our domain, which is a pair of sets, and our codomain, which is a pair of sets. And we think of our domain as the inputs and our codomain as the outputs of this controlled process or controlled system. Each input and output comes in these pairs of an action and a reaction. And so the first thing that our system will do, so our system also has a state, and then it also has either a way to change the state or a way to evaluate hypothetically what a change would do to the state. So the first thing a system does is it takes an action from its input and it uses its current state to determine an output action, which it puts out to the environment. But then, presumably, the environment reacts to this output. And so that comes in on the output reaction wire. And now our system takes the same input action it has. It's still allowed to use this. It's kept it around and made that little copy in there. And it's going to use that together with the current state to produce two things. One, it's going to send a reaction, an input reaction back upstream to whatever supplied it with the input action in the first place. And this is giving you a sense of how these things compose. But the second thing is it's going to change the state. So that's the changes. I write TS, you can think of it as a tangent bundle. In the case of that you're using systems of differential equations, it will literally be the tangent bundle. Or it might, so this is the case if you're doing a dynamical systems theory, it will give you a change of state, that's its updated state. Or if you're thinking more of game theory, it won't give you a change of state, but what it will do is give you a utility function, which will, you can think of it as a way of taking a possible change that you might make a state and evaluating it, giving you a value, a utility for it. And so if you think of, if changes are like the tangent bundle, then valuations are like the cotangent bundle. So they give you a value for every possible change you might think. And one of your systems is going to do these things. So this is the point of view that cybernetic systems or controlled systems are parameterized lenses, is the point of view taken in Capucci, Gavrinovich, Hedges, and Reichel's paper on towards the foundation of cybernetic systems. And it's also the point of view taken in Shapiro and Spivak's work on dynamic categories and dynamic operats. So they don't write it this way, but by transposing a few adjunctions, you can see it this way. So they write, they have one of their parameterized systems is a coalgebra for the Hom polynomial functor between two polynomial functors. Now, polynomial functors are lenses of a specific sort. I'm going to come to that soon. And so because this is a Hom, we can use the Hom tensor adjunction to flip it over and see that it's in fact a parameterized lens. So let me tell you a bit. I'm going to do a bit of background here to tell you a bit. how I think about these things. Here's what a lens means for me. It is the definition of a functor lens or generalized lens due to David Spivak. So if we have an index category, then the lenses is the category of lenses is the Grothendieck construction of the pointwise opposite. So you take all the categories that you get in this indexing, you take their opposite, you take the Grothendieck construction of that. And so what is that? Well, it's a lens consists of a pair of maps here, one on the bottom and one on the top. And the one on the bottom goes forward, and then one on the top works like this. You take the second thing on the top and you pull it back, and then you take a map from that into the first thing on the top. So this is the bidirectional information flow of the lens. And so there's a usual Grothendieck construction, and a special name for that in my book. I call them charts because the way the role they play in systems theory. And we can organize the two of these into a double category, which I call the Grothendieck double construction, not to be confused with the double Grothendieck construction. So this one takes in an index category, no double categories in sight, but it produces a double category. And what it produces is a double category of squares like this. So in the ordinary Grothendieck construction, both maps go in the same direction, that's forwards, right? And then, so we put those horizontally, and vertically, we're going to put the maps that go bidirectionally, the lenses. And the double category is thin, which means it has at most one square in any signature. And so it has a square if and only if both of the constituent squares commute. So in the bottom, we really get a square. And then in the top, we have to pull everything back to the right place, and then we can get a square, and then that's the one that commutes there on the right. And so these squares are useful. They give, for example, we've seen that systems can be seen as sort of a certain kinds of lens. And actually, I think I have a slide on this. We have, so now this is a little bit of my book, the point of view I take in my book, is that what we can, it doesn't take too much data to set up what a lot of people think of as a systems theory. So there's a lot of different ways to do systems theory. Matteo was telling us all about this in his talk. But one of the very common patterns, one of the, I would call it a doctrine, to use the categorical logic terminology of systems theory, is parameter setting using lenses. And so a parameter setting systems theory is going to be this index category that just lets us build lenses, and a section of its Grothendieck construction, which I've written T here. And that, in a way, is going to tell us what a change of state means. So the way to think of this is here, B is our state spaces and our output spaces, like what the variables take place in. And E is our bundles. So in general, the changes that we have will be a bundle over the states. For example, if you're using differential equations, a differential equation is a vector field on a manifold. So that's a section of the tangent bundle. And that's a certain kinds of lens out of the tangent bundle, I should say, which is what we see down here. A system is a lens of this sort. So if you can see, it splits apart into two maps. One is we expose some variables out of the state space S into some output space O. And the second is we pull back the inputs. And so if you think about what the pullback does, it takes pairs. So we take a pair of a state and an input, which is valid for that, which is bundled over the exposed variable we have there. So an input that's valid in that state. And we give a change of state that's an element of TS. So this pattern works for more machines in the deterministic case, and the Markov processes in the non-deterministic case, the systems of differential equations, if this is literally manifolds and vector bundles and tangent space, and so on. So a controlled system is going to be a paralens of this sort, where the parameter has a special form here. It's STS. And what that means, as you can see, is in general, if this is monoidal, a monoidal system theory, everything in sight is monoidal. And in a monoidal systems theory, we can express a paralens, and it will be of this form. So we're going to take we think about things really different. If we just had a system, we thought about inputs and outputs coming on top, one on top of the other. But now with a control system, we think about actions and reactions, as I described it before, and inputs and outputs play this different role. So no longer does the system, is the update taking in an input, it's taking in an output reaction. So it's just a different way of thinking, but it turns out to work in the way we actually use these things. So, okay. So are there any questions before I go on? We got a little more background here. So here's why do we need these double categories of maps. So this is one of the double categories that Matteo was describing of controlled of maps between controlled systems here. So here's our controlled system up above. Now suppose that we have an element of each of these wires coming in and going out. So we have an input action, we have an input reaction, we have an output reaction, we have an output action. Then we can say what it means for a state to be steady. And it's steady if on our chosen input action, it gives our chosen output action. That's not really sort of a crucial feature. That's just letting us index the steady states by what they output. And the really crucial one is that on its update, it produces exactly the tangent functor applied to S when it's considered as a map from the terminal object, or the unit, if it's a monoidal thing. And so what that says is that if it's really tangent bundle, it will produce the zero vector. If we were in deterministic things, it's going to produce itself. And that's what it means to be steady. So it's the differential of the state at zero at the point is S is zero, or the next state we transition to is the state itself. So these equations are written out in the following square on the bottom right. So if we have that following square in the double category of arenas, the Grothendieck double construction that I mentioned before, then that such a square commuting, or such a square being in the double category, is equivalent to those two equations up top. And so we can make a new double category where it looks like a parameterized version of this arena category, where now on the verticals, instead of just having lenses, we also have these parameterized systems. We have these parameter spaces, these parameter systems there. And we have these maps, not just the squares now. This is no longer a thin double category. The squares are actually filled by maps between the systems. So this is a way that it shows up in systems theory. But it also shows up in dynamic operad. So I thought I would talk about that quickly here. I'm not going to go too much into what a dynamic operad is, but it's a notion due to Brandon Shapiro and David Spivak. And so we can define it in any monoidal systems theory now, given that we have this kind of double category here, which should be called org. That's to steal a terminology from Brandon and David. So if we call this double category where we have the vertical ones are paralenses where we're parameterized by these state spaces here, and the horizontal ones are maps, are charts, but the middle one is actually of the form something on states and T of that thing on states. So this is a morphism of systems, as it is a morphism of controlled systems. Then we can define a dynamic operad to be a operad enriched in this double category, so long as it's a monoidal double category. So that requires a symmetric monoidal systems theory, I should say, or at least a braided monoidal systems theory. We'll come back to that. So this is the exact same notion as in Shapiro's Spivak, but it is not the exact same double category. It's in fact a variant of it because they have different horizontal morphisms, but the same two cells with identity horizontal morphisms. So it turns out that the definition of operad is the same, but we get different maps. And so I want to just advertise this one a little bit here, which is that they give an example of a dynamic operad, and it's a prediction market, and you can build one for any set. And this assignment of sending a set to the prediction market dynamic operand on it is functorial when you land in this variant of org. And this appeared in the triple category thing on one of the sides there. So we're gonna see that. But I should move right along to actually telling you what the para construction is. So that's the why. That's why I'm in it. But I think this story is cute on its own. So now we're just going to do a little math. So okay, so the para construction, what is it? You take a monoidal category, and we're going to give you a category, and the maps are parameterized maps. So if we use string diagrams to draw a monoidal category, then the maps in the para construction look like these boxes, where you have the parameter coming in vertically. But you always think of the parameter as coming in from the input side. So I know that when you draw vertically, it's not sort of clear, but if you label the arrow and you note that the arrows always must point left to right, then there's only one way to interpret this picture. It must be that the P comes as an input because it's going into the box F. So that's like one way to think of it. And so we need two features here, sort of, to make it work. We need the identity map and we need the composite. And the identity map here is going to use the fact that when you take a sort of trivial parameter space, it doesn't really change what you have here. And the composite one is we're going to use that sort of this law of the associative law of a monoidal category to act first on to use the first parameter to act and then use the second. And if you look at the string diagrams, it's really clear what this is. You just put the boxes together, and then if you look coming in, now you have both wires coming in, so it's their product. So the problem with what I've just told you is that this is not a category because it's not associative. This composition is not associative, right? And the reason it's not associative is because this monoidal category isn't strictly associative. So we need to quotient out by something. And what we're going to do is we're going to quotient out by reparameterization. So we have two choices here. A reparameterization, I should say, is just like pre-composing by a map into the parameter object. And so our choices are we can quotient out by any map. And this is the choice that you would come to, I think, if you're an optics person, because you can express it as a certain co-limit here. It's like feels very optic-y. Or you could just quotient out by isos, which is the usual option. So in that case, now we set equal to maps when they have this when they are have the isomorphic parameter sets, and therefore now it's associative because of course it's up to isomorphism. Our monoidal category has an associative multiplication. Now clearly these are both shadows of an underlying bicategory. And that bicategory actually has two cells where the two cells are reparameterization. And that is a way you can go, and that has led to some fruitful generalizations of this notion. In particular, if you take that point of view seriously, you can see the para construction as a form of Grothendieck deconstruction of bicategories, which is a cool story, but not the one tonight. The one I'm going to talk about is we're going to do that trick where we look at a bicategory and we think, oh boy, I wish I had a double category. So here we go. So this is a double slide. First of all, I just want to note, we don't actually need a monoidal category here. We just need a way for our parameters to act on our spaces. So our parameters could be qualitatively a different kind of thing, and they can act monoidally on our spaces. The most common way this shows up, and the way I'm going to use it tonight, is restricting, when we just restrict to a certain specific subcategory, or restrict along a pseudo-monoidal functor. So we only use some objects to act. And so an actegory is an up to coherent isomorphism action of a monoidal category. And so the two laws, I'm going to name them here. One is this sort of version of associativity, which I'll call rho, and the other is the unit action law, which I'll call iota. And the paramaps here use the dot product, which is the action here, but it's everything looks the same. So now here's the double category we get if we take into account reparameterization. So we're going to define this double category. Its horizontal category is going to be the original category. The vertical category is going to be para. And the two cells are going to be squares of this form. So if we have this horizontal alpha and beta, and we have this kappa, which is a reparameterization, a map from P1 to P2, then we can organize that into the square, and this square on the left in the double category means that square on the right commutes in our category C that we're acting on. And so one thing I want to point out is that Liz looks like the para arena that I described before, but it's not the same thing. So the reason it's not the same thing is because if we applied this to lenses, say, then everything in sight would be lenses. And we want to have two different kinds of morphisms. And so this is sort of what Matteo was saying at the end of the talk, is that we're forced to go into another dimension to do this. And so we'll see that. Okay. So this is what we're looking for. What we're looking for is to take an actegory and produce a double category. And one thing I would like to note here is that it's nice about this signature for the para construction is that actegories are these pseudo actions of pseudo monoids in cat, and double categories are categories internal to cat. So we've turned this signature of para into something that takes cat, the two category of categories, as a parameter, and we'll use that later. But before we get there, how should we think about this? So let's be kind of naive here and think about what are the morphisms? Well, a morphism in para takes a parameter and an object as a domain and multiplies them or acts, and then as a codomain, it takes just another object. So we can write that definition down for the arrows as a pullback. And that's the pullback I've drawn here. So the objects of that pullback, which is the comma category over the action, are precisely the morphisms of para. And the maps are the squares from the double category we wanted. So it seems like this is a good start. And what we can do here is we can complete this pullback diagram by adding little legs to it and see that it's a composite of spans. So the thing to note is we're looking for a double category, and a double category, well, if you step back a bit, a category is a monad in the double category of spans of sets. And I'll just say the bicategory of spans of sets, just to be simple here. And it's true also that a double category is a monad in the bicategory of spans of categories. But that's a strict double category. And we are going to end up with a weak double category because these parameters, we have objects as our morphisms here, our parameters objects here kick around, and the composition is only going to be associative up to our isomorphisms. So we need a pseudo-monad in a tri-category of spans of categories, and that's a pseudo double category. So now when we look at these two spans, we can see that they each actually have a monoidal monad structure already, meaning that there are certain kinds of double categories. So on the left, we have what I would call I'll start on the right. On the right, we have the double category of squares in our original category. So that's where that square, the commuting square there on the bottom right, that is a square in the double category of squares, whose horizontals are the morphisms of the category, whose verticals are the morphisms of the category, and whose squares are commuting squares in the category. And on the left here, we have the Cayley double category or action double category of the action. And this is a thing you probably have heard of in decategorified terms. It's an analog of the Cayley graph. So if you have an action of a monoid on a set, you can form a category. Well, when it's called a Cayley graph is often called a graph, but you can really compose the morphism, the arrows in the Cayley graph. So it's actually a category. And that's called the action category or Cayley graph. So this is a version of that. So what it looks like we're doing is we're composing two monads in this tri-category, two pseudo-monads. So we should look for a distributive law because that's how you compose monads. So that's why we're going to look for a distributive law here. So first, I got to tell you what the tri-category is. So it's a special tri-category here called F span of cat, and F stands for fibration. So here, the left legs of our spans are going to be Cartesian fibrations. If you're very pedantic, they're Cloven fibrations, Grothendieck fibrations. And the two cells are going to be diagrams of the sort drawn there, which commute strictly on top, and where the middle morphism is a Cartesian fibration. So that top part of the diagram says that F is a Cartesian map. So it has to preserve lifts, or it doesn't have to preserve lifts, it has to preserve Cartesian morphism. And the bottom is going to commute only up to naturalized morphism. So that's that cell there. And the three cells are going to be naturalized morphisms between the F's, which make the appropriate diagrams commute. And everything is composed by strict pullback. So, so this actually is categorically correct because Cartesian fibrations are already isofibrations. So the strict pullback is already the two pullback, which is a useful feature. What that means is we can get rid of like one level of coherence hell in working here. So just one, but it's enough. Okay, so as the example here, this is what the double category of squares looks like, is a pseudomonad in this setting. It actually is a strict monad because composition in because it's a strict double category. So what it is we take this pullback here of the two spans, and then we map into the span itself, and that gives us our multiplication. So in this case, when we take the pullback of the double category of this span here, we get a map in whose codomain is the domain of another map, and then we can just compose them, and that's our multiplication. And the unit here of this monad is going to be the identity, and these of course satisfy the monad laws because the monad laws are the monoid laws, and these are the associative and unity laws from the category. So as a double category, thinking as a double category, what this is squares. The Cayley double category, on the other hand, is going to be defined like this. So we're going to think about it as is this way. Its horizontal maps are going to be just maps from C, and its vertical maps are going to be elements of our monodal category that acts, and they're going to go between an object and the object, the acted on version of that object. So they just sort of point to where the object M1 acts. And this is not a strict monad. This is a pseudomonad because M is only a monodal category. And so the way this acts is if you take that pullback, you can see that it's given by, since one of these things is a product projection, the pullback is just given by adding another product here. So you can see that it's just given by component-wise multiplying an M. And so that's a very simple thing here. And you can see that at the bottom, what we get is precisely that cell we needed before, which is rho. So rho is this associativity for the action. On the other side, the unit of the action is the unit of the monodal category. And in fact, the pseudomonad structure on this, with all its coherences, is exactly the structure of the actegory in the first place. So what we can note here is that a pseudomonad in F-span cat, whose left leg is a product projection, is precisely an actegory. So the fact that the top cells commute tells us that this is happening just in the M component. So it's just giving M the structure of a monodal category in such a way that the right leg of this span becomes the action. So that's kind of fun. So we're now going to put these together into our distributive law. So the way the distributive law works is it has a signature. Here's the diagram. And what we're going to do is we're going to take a map from C prime to C. And then we're going to take this pair M comma C. And we're going to multiply F by M, act on F. That's it. That's all it is here. And so this is going to swap things around here. And this is going to have to satisfy 4 axioms. I have them on the next slide. And it's going to have to satisfy 9 coherence conditions, which are due to Marmolejo. So I'm very glad that Marmolejo has this paper writing about the necessary coherence conditions for pseudomonads, because that was scary at first. I mean, it's still scary, but all right. So this is how it works, right? If you have these two, this is how the resulting composition we're going to get on our pseudomonad, our composite, our para will work, is we take these two things, right? And we're going to use the distributive law on the middle pair here. So that's going to take M2 and it's going to act on F. right? That's what the distributive law tells you when you compose two monads. You take the composite of the two of them, the middle two are in the wrong order, you swap them over, and now you can multiply on both sides. And that's precisely what we do here. And nicely, the row actually just appears just perfectly to tell us that we used it first, but this is where it appears. So, all right. So the actual laws themselves they're not so bad in this case, but there's a little generalization on the next slide that in that case they're quite bad. That's taking a little bit to slow through. But the unit laws are pretty simple. The first one just says that the Cartesian lift of an identity is an identity. What I mean by that is that if we act on an identity, we get an identity, or by n. So that's pretty simple. And the second one is that if we re-index along f, take 1 and we re-index it, it's still 1, and that is true. If we pair 1 with anything and we pair it with something else, it's still 1. So those are trivially and strictly commutative. Now 3 and 4 are the meat of the distributive law. I've written them on the right in abstract terminology, just so you can see what we're doing. And so in 3, what you can see is it's the functoriality of the action. So it's not so bad, and it's also strict. And this is one of the reasons why this case is actually quite nice of an actegory. And in 4, we get our first non-strict cell for our distributive law. So this is where we start to have to actually check stuff, the coherence conditions. And this is the one that says that well, it effectively says that if you tensor and then act, it's the same as acting and tensoring again. So it turns out this is just row again, but it's on the action on arrays and not on objects. Okay, just going to keep going. As an aside, we can note that lambda, I was using these terminology of Cartesian lift. I think I maybe put that a little out of order here, but lambda is the universal Cartesian lift of this projection. So this projection is a Cartesian functor. A Cartesian lift here is really simple. It's just given by, if we have a map C prime to C, and we have an object MC, which lives over C, then the Cartesian lift of that map is just the map M comma that map. So it goes from MC prime to MC. So the pullback is just change the second component. So it's that's in a way why it's so strict. But we could do everything we did up above for any pseudomonad in F-span cat. So let me call a pseudomonad in F-span cat a dependent actegory. And the reason I call it that, Matteo also has suggested the terminology fibraction, so which is quite nice. But the terminology is not fixed here. But the reason I call it that here is because if you have here, what it says is that the parameter space actually can depend on the input element you're currently at. And so you actually can have a varying category of parameters that depends on your input space. And in this case, the left leg becomes this vibration. It's just sort of telling us it's like this index category. Everything on the left leg side is strict, remember. So it's really like we're working in the index category, right? Not like this, up to equivalence vibration set. And the right one becomes this action, and this action takes something that's a parameter space that's valid for C and gives you a new object that's acting. And the distributive law here we can define in complete generality as taking the universal Cartesian lift. So this is really fun equivalent definition of Cartesian vibration, which I learned from Emily Real and Dominic Verity's book on infinity categories, which is that if you have the induced map from E, the arrow category of E, to the comma category over the Cartesian to the vibration pi, if that has a right adjoint, right inverse, which is the universal Cartesian lift, then that's if and only if pi is a Cartesian vibration. So we can just post-compose that by an appropriate map, putting us in the right place, and that's our general double category. So this actually doing this one out is a little bit tricksy, because a lot of the things that were strict in the case of the nodal category are no longer strict. They're just there's a unique map which is the sort of unit of this adjunction here, the adjunction that defines the Cartesian vibration. And it becomes an isomorphism in all these cases. And that just sticks around in all your things. So it's a little trickier there. So that's slowing things down. But in principle, it should work in that case. So if you run through what this construction says, in the case that C has pullbacks, then we can actually flip the order. We get a different double category. I can't off the top of my head think about what this looks like as a double category. But if we just flip the order of domain and codomain, now codomain is now a vibration because C has pullbacks. And if we run this construction, the para construction, on this, using this idea, we get span. And the way we do that is we take this comma category here. In this case, it gives us the corners. The universal Cartesian lift is in fact taking the pullback. And then we project onto both of our domains. We take the back of a pullback, and that is indeed how you compose spans. So like this is happening in the middle of your span. So this says that the para construction of this thing here is span. And so we can think of spans as a para construction. And one way to think about that is that if we imagine that this codomain vibration is giving us dependent types, then you can see that this is very much a dependent actegory where the dependent product here is or dependent sum. The action is we take pairs, but now the parameters can depend on which of our particular input variables. So I hope that you can see that in that bubble there, it actually looks a lot like para, but now our parameters can depend on our particular input variable. So one thing, I don't know any other examples, and in particular, I don't know a non-Cartesian example. Now it's kind of where something about this has to be Cartesian because we have these Cartesian vibrations around. But I don't know like an example where you just have a monodal, like monodal structure on lenses is not Cartesian, right? It's Cartesian for charts, but not for lenses. So I don't have an example of dependency where it's non-Cartesian. So if you could think of one, I'd love to know. Okay. So now we can talk about where the para construction actually happens. And the thing to note here is that the para construction only used pullbacks of isovibrations in cat. And we only needed these arrow category in our category. So we only needed to have powers by the arrow. So we can do this in what I would call a one cosmos, which is sort of a de-infinityization of a real verity infinity cosmos, where we just have this structure we need to do this. And then we can define F-span, we can define Cartesian vibrations, we can define the arrow category, and we can run this argument in that place. So in particular, if we do this to monodal categories with pseudofunctors, we actually get the monoidal structure on para when the action when the monodal category is braided and the action commutes appropriately with the braiding. So this is a nice thing. So the original idea is like almost always you want symmetric monodal categories, and in that case, para actually also has a monodal structure. But if you write down what it needs to happen, you notice that things have to move around for it to be written in the right order. So we do that. And if we use K to be the strict double categories where we use the vertical transformations, then one of those strict double categories with vertical transformations was arena. So we can get a triple category, para arena, where by triple category, I mean a pseudo, a weak internal category, a pseudo monaded span, and this kind of spans of strict double categories with vertical transformations. So it has these vertical structure isomorphisms here. So it's only actually weak in one direction. And we can apply this now to this particular actegory internal to double categories. So if we have a monodal systems theory, then arenas, which is this double category of lenses and charts, excuse me, then arenas are monoidal as well. And so we can restrict, and the functor of changes here, T, tangent bundle functor, is a monoidal functor. So restricting the monoidal product of arena to this gives us an action of our spaces on this. And if we apply para arena to this, we get this somewhat degenerate triple category, which contains all these, well, quite a few of these structures that we were talking about before. So in particular, it contains on the vertical and horizontal directions, it contains arenas again. On the verticals and transverse directions, it contains, on the transverse direction, the new direction we added, it contains our control systems. And on the vertical transverse, it contains these sort of reparameterizations, these hooking ups. So when you do this stuff, you know that composing with lenses is the way that you wire together systems. So these are the rewirings of systems that are happening vertically, transversely, and then transverse horizontally are maps of control systems. So in particular, the variant of org I was talking about earlier, which appears in both systems theory and in Capucci et al. Cybernetic systems theory, and in Shapiro Spivak dynamic operands appears there on the bottom. And if you just did it to arena acting on itself, you would get that full triple category that Matteo showed, and I had at the beginning of the talk. So, okay. So thank you very much. That's all I got.
Okay, thank you, David. That was a really nice talk. Does anyone have any questions, or if you have a question, just feel free to raise your hand or jump in. So, I mean, I guess I'm curious to know if there's like a nice way to identify which double categories arise from these distributive laws with the arrow category.
Yeah, that's a great question. There's some obvious features, as Matteo was pointing out. They all have companions in the right way.
Mm-hmm.
And it's not. I don't think that just having companions is enough, because I actually think I'm not sure about this, but I think that being a pseudomonad where your left leg is a vibration is just the same thing as having companions. And so any one of those has companions, so it's not enough to cut you down to the ones that come up from the distributive law, but they are quite special in lots of ways. So that's very interesting.
Yeah, cool. Are there any other questions? Okay. Well, there's a question maybe in the chat.
May I say a few words?
Yes, go ahead, please.
In fact, it's not exactly on this conference, but on the workshop in general. And I would say that I have found it wonderful, and I would like to thank the organizers who have united so many interesting things on double categories. And I am especially interested in double category, since as René Paré has said in his conference, the double category were introduced by Charles Erasman, and we had much work on them. They were introduced in the 60s, in the early 60s, and we had in the 70s, we have made many article papers on this double category, in particular on monoidal structure, on the categories of multiple categories, and so on. And I am very interested in things. But I would like to say that, in fact, the first definition given of a double category was not through the fact that it's a category in cat, an internal category in cat. In fact, the first definition was given by Charles in 61 from the double category of square and the double category of quintets with categories, functors, and natural transformations. And in fact, the definition was then a set theoretical definition saying a double category is the data of a category as it was defined at that time, on which there is defined another structure, and that in the double category it was two different structures of category given on the same set. And from the example, he realized that these two structures were related by a kind of distributive law, and so he defined what was this law, and it led to the fact that the source and target and composition law of one of the category were functors for the other law. And this reminds of other kinds of this kind of things which he has defined before for topology, where topological defining of topological category for his works on differential geometry by the data of a category on which there is topology with the source, target, and composition, which are continuous. And so this led to his definition of structured categories, which were published in 63, and which later on were called rather internal categories, and in fact, which also led him to the notion of sketches, which generalize these notions. So I was very pleased to see that this notion of double category, which was initially coming from the so simple a category of squares, led to so interesting things, and really I am very interested by this conference, and I hope to look at the different slides of them when they will be accessible, and I'd like to come back to my first studies in these double categories. So I thank very much all the participants, all those who have spoken and who have given so interesting results, and naturally the organizer who had the idea to unite so many people on such particular subject, that virtual double category. So thanks for all.
Thank you so much. Okay, that was really nice. Thank you.
Great. That's nice. Bryce, do we have time for me to answer a question in the chat?
Yes, please go ahead.
So this is for Nathaniel. So I didn't mention it, but it is. I mean, I don't know if it's true what it means in general, but I believe that this is a paper of Eugenia Cheng's about the distributive laws of categories, or factorization systems. And in this case, the factorization system is the one, the sort of obvious one you would write down, where you could just you could either act on you could have a map that doesn't act on the parameter and the one that just acts on the parameter. So that's sort of what you get when you work it out. But I don't know what it means to do it, what it means for the double categorical situation, but presumably it's the same thing. So
yeah, if I may add, in the double category, you get para, like the para double category. That factorization system gives you some, I think Schulman calls them restrictions. So it's not a full conjoint structure on your, sorry, I'm probably using the wrong word. It doesn't give you conjoints for every tight arrow, sorry, for every loose arrow, but it gives you some of them. So pictorially, it means that if you draw a parametric morphism as a box with two arrows going in, one on the left, one on top, and an arrow going out from the right, then the factorization tells you that you can bend the top arrow, like curve it slightly, and pretend that your morphism is not parametric, but receives P action A as a full input. I don't know if I managed to render this in words. It tells you that every parametric morphism can be seen as a non-parametric morphism if you pre-compose it with like this bend that makes the blue wire there bend horizontally to become a green wire, basically. So these things are like kind of like very weak prior equipments, extremely weak prior equipments.
yeah, they just have the companions on one side, right? I guess it is a different thing, right? Yeah, because you can actually, maybe that is an answer to Bryce. Understanding what exactly that is an answer to Bryce's question.
Yeah,
it's probably this extra factorization system is what you get, and then the fact that plays well with the companions that you have is what everything factors as a companion as well, which is fun actually, because don't have 2 minutes, sorry, Michael. But it factors the double category of arenas is also something you can the Cartesian vertical factorization of the underlying index category you started with arises as the companions and contours in that double category. So it's fun that you can sort of claw back the data by looking at these factorization systems, or claw back the factorization system by looking at the double categories.
Okay, thank you. I think it's time to thank our speaker again.